Hi, this is Schwartz from MasterMathMentor.com. This is video BC25. The topic is Taylor and Maclaurin series, and it covers the BC manual pages 122 and 123. We will now go back to when we first started to talk about series. Back then, we studied Taylor and Maclaurin polynomials, and we will now extend our knowledge to Taylor and Maclaurin series. So we start with some convergent power series centered at C with a radius of convergence R, and we will take successive derivatives and evaluate them at x is equal to C. So we start with our series f of x is equal to a sub 0 plus a sub 1 times the quantity x minus c plus a sub 2 times x minus c quantity squared plus a sub 3 x minus c quantity cubed plus a sub 4 x minus c quantity to the fourth plus dot 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 plus a sub n quantity x minus c raised to the n plus dot dot dot. We will first look at f prime of x. That is equal to a sub 1 plus 2a sub 2 times the quantity x minus c plus 3a sub 3 quantity x minus c quantity squared plus 4a sub 4 quantity x minus c quantity to the cube plus dot 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 plus n a sub n times the quantity x minus c raised to the n minus 1 plus dot dot dot. And if we evaluate this at C, all the terms except the first drop out. So f prime of C is equal to a sub 1. And we could then say a sub 1 is equal to f prime of C over 1 factorial. Let's look at f double prime of x. That will equal 2a sub 2 plus 6a sub 3 quantity x minus c plus 12a sub 4 quantity x minus c quantity squared plus dot 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 plus n times n minus 1 a sub n times x minus c to the n minus 2 plus dot dot dot. Again, when we evaluate this expression at C, all the terms except the first drop out. So f double prime of C is equal to 2a sub 2, meaning that a sub 2 is equal to f double prime of C over 2 factorial. Let's find f triple prime of x. That will equal 6a sub 3 plus 24a sub 4 times the quantity x minus c plus dot 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 plus n times n minus 1 times n minus 2 a sub n times the quantity x minus c to the n minus 3 plus dot dot dot. So f triple prime of c will just be the first term in that series, which is 6a sub 3. And therefore a sub 3 is equal to f triple prime of c over 3 factorial. Let's look at the fourth derivative of f. That will equal 24a sub 4 plus dot 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 plus n times n minus 1 times n minus 2 times n minus 3 a sub n times the quantity x minus c raised to the n minus 4 power plus dot dot dot. So f fourth derivative at c is simply 24a to the fourth, and therefore a to the fourth is equal to the fourth derivative of f at c over 4 factorial. Following the same pattern, the nth derivative of f at x is n factorial a sub n plus n plus 1 factorial a sub n plus 1 times the quantity x minus c plus dot dot dot. We don't really care about any term other than the first because when we plug in c, we were going to get 0. So the nth derivative of f at c is n factorial a sub n meaning that a sub n is equal to the nth derivative of f at c over n factorial. So if a function f has derivatives of all order at x is equal to c, then we look at the summation n equals 0 to infinity of the nth derivative at c over n factorial times x minus c to the n. When expanded, this is f of c plus f prime of c times the quantity x minus c plus f double prime of c over 2 factorial times x minus c quantity squared plus f triple prime of c over 3 factorial quantity x minus c quantity to the third plus plus the nth derivative at c over n factorial x minus c raised to the nth plus . That is called the Taylor series for f of x at x is equal to c. Now, if c is equal to 0, then our series, summation n equals 0 to infinity of the nth derivative at c over n factorial x to the n, which can be expanded into f of c plus f prime of c times x plus f double prime of c over 2 factorial x squared plus f triple prime of c over 3 factorial x cubed plus plus the nth derivative of f at c over n factorial x to the n plus is called the Maclaurin series for f of x. So to find a Taylor series for f at x is equal to c, we follow this procedure. We first find f of c and then differentiate f of x several times to find f prime of c, f double prime of c, f triple prime of c, etc. And then attempt to establish some pattern to find the nth derivative at c. We then use those values that we just developed to form the Taylor coefficients, which is the nth derivative at c over n factorial, and create the Taylor series, which is f of x will equal f of c plus f prime of c plus times x minus c plus f double prime of c over 2 factorial x minus c squared plus f triple prime of c over 3 factorial x minus c raised to the third plus the nth derivative at c over n factorial x minus c raised to the n. We then must use this nth term of the Taylor series to find the radius and interval of convergence. Let's go through this procedure of creating a Maclaurin polynomial for f of x is equal to cosine of x and find the interval of convergence. Since it's a Maclaurin polynomial, we will be evaluating f and its derivatives at 0. So if f of x equals cosine of x, f of 0 is equal to 1. F prime of x is equal to negative sine of x, and f prime of 0 is equal to 0. F double prime of x is equal to negative cosine of x, and f double prime of 0 equals negative 1. F triple prime of x is equal to sine of x, and f triple prime of 0 is equal to 0. The fourth derivative of f of x is equal to cosine of x, and the fourth derivative at 0 is 1 again. The fifth derivative is negative sine of x, and the fifth derivative at 0 is equal to 0. We now build our Maclaurin polynomial using our coefficients. Cosine of x will equal 1. There is no x term. And then it will be minus x squared over 2 factorial. There is no x cubed term. Plus x to the fourth over 4 factorial. There is no x to the fifth term. And minus x to the sixth over 6 factorial plus ... We then have to build this nth term, and we see that it's alternating, which will give us a negative 1 to the n. X will be raised to the 2n, and whatever the power of x is the coefficient with a factorial, so that will be a 2n factorial. So our series can be written as summation n equals 0 to infinity of negative 1 raised to the n times x to the 2n over 2n quantity factorial. We now would like to know how accurate this Maclaurin series is in evaluating cosine of x, meaning can we use any value of x in this expression and be confident that we will get an answer that will be close to cosine of x. So we use our ratio test and look at the limit as n approaches infinity of the nth plus first term over the nth term. This is negative 1 x to the 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. And that is the limit as n approaches infinity of the absolute value of x squared over 2n plus 2 times 2n plus 1. And this is 0, which is less than 1, telling us that our radius of convergence r is infinity, making the interval of convergence negative infinity to infinity. What this is saying is that we can now plug in any value for x to evaluate cosine of x, and if we use enough terms, we know it will be converging to the exact value of that cosine of whatever value we chose. As a caveat, it is important to understand that this Maclaurin series for cosine x may not actually converge to cosine x because the derivatives are only evaluated at one point. That is, x is equal to 0. Perhaps some other function will agree with the values of the nth derivative at 0, but disagree with other x values. In order to show that the Taylor series for f of x equals f of x, we must show that the remainder, using the Lagrange error, is 0 for all x in an interval, and we will not spend the time in doing that. So for the functions that we use in our illustrations, we will assume that the Taylor series for f of x actually does equal f of x. For f of x is equal to 1 over x, we are asked to find the Taylor series centered at 1 along with its interval of convergence. Since f of x is equal to 1 over x, f of 1 is equal to 1. F prime of x is equal to negative 1 over x squared, and f prime of 1 is equal to negative 1. F double prime of x is equal to 2 over x cubed, and f double prime of 1 is equal to 2. F triple prime of x is equal to negative 6 over x to the fourth, and f triple prime of 1 is equal to negative 6. The fourth derivative of f at x is 24 over x to the fifth, and the fourth derivative at 1 is 24. The fifth derivative of f at x is negative 120 over x to the sixth, and the fifth derivative at 1 is equal to negative 120. We can now write the Taylor polynomial as 1 over x equals 1 minus quantity x minus 1 plus 2 quantity x minus 1 squared over 2 factorial minus 6 quantity x minus 1 cubed over 3 factorial plus 24 quantity x minus 1 to the fourth over 4 factorial plus dot dot dot. When we simplify, we find that all the numbers disappear and we're left with 1 over x is equal to 1 minus quantity x minus 1 plus quantity x minus 1 quantity squared minus quantity x minus 1 quantity cubed plus dot dot dot. And we have enough evidence now to write the nth term as negative 1 to the n times x minus 1 to the nth power plus dot dot dot. To find the interval of convergence, we use the geometric test and find out where negative quantity x minus 1, the absolute value of that is less than 1, giving x is between 0 and 2. If x is 0, our series turns out to be 1 plus 1 plus 1, which is divergent because of the nth term test. If x is 2, then our series is 1 minus 1 plus 1 minus 1 plus dot dot dot, and this is also divergent by the nth term test. So the interval of convergence is the open interval 0 to 2. Number 3 is different from the previous problems. Rather than taking some information and finding the Maclaurin series, you are given a Maclaurin series and then asked to find some information. You are told that the Maclaurin series for f of x is given by summation n equals 0 to infinity of -1 to the n times quantity n plus 2 times x raised to the n over n plus 1 factorial. We are asked to find the 25th derivative of f at x equals 0. We start by expanding the series. F of x is equal to 2 minus 3x over 2 factorial plus 4x squared over 3 factorial minus 5x cubed over 4 factorial plus 6x to the 4th over 5 factorial minus ... We then need to take derivatives. The reason for this is that we will eventually need to take the 25th derivative. We are not going to do this 25 times. What we are hoping to do is to see a pattern when we take our derivatives and plug in 0. In order to do that, we're going to need to look at a few terms to establish our pattern. So f prime of x is equal to -3 over 2 factorial plus 8x over 3 factorial minus 15x squared over 4 factorial plus 24x cubed over 5 factorial plus ... And f prime of 0 is equal to -3 over 2 factorial, which is -3 over 2. We take the second derivative and get 8 over 3 factorial minus 30x over 4 factorial plus 72x to the 5th over 5 factorial plus ... Again, plugging in 0, we only have to worry about the first term, which is 8 over 3 factorial, which is 8 over 6, reducing to 4 over 3. The third derivative is -30 over 4 factorial plus 144x over 5 factorial. We don't need any more terms because the third derivative at 0 is simply the first term, -30 over 4 factorial, or -30 over 24, or -5 over 4. Hopefully you begin to see the pattern. The fourth derivative at x is 144 over 5 factorial plus all the other terms, which again will be 0. So the fourth derivative at 0 is 144 over 5 factorial, which reduces to 6 over 5. So our derivatives appear to be alternating, with the even terms being positive. So the nth derivative at 0 will be -1 to the n. And since the number upstairs is 1 greater than the number downstairs, and for the third derivative we had a 5 upstairs and a 4 downstairs, for the fourth derivative a 6 upstairs and a 5 downstairs, we will have an n plus 2 over n plus 1. So the 25th derivative at 0 will be -1 to the 25th times 25 plus 2 over 25 plus 1, and our answer is -27 over 26. This is the type of problem that will show up on the AP exam in the multiple choice section. Suppose we had nothing but a 4-function calculator: addition, subtraction, multiplication, division. No trig, no square roots. And we wanted to calculate 2 inverse tangent of 1/2. Could we do it? It might surprise you to know that we can, and we can get extreme accuracy, and the answer will be approximately 1 minus 1/12 plus 1/80 minus 1 over 448, and that will give accuracy to 3 decimal places. Suppose we wanted to find the value of e raised to the I pi power, where I is an imaginary number. Just thinking about this problem should make your head spin. What does it mean to raise e to an imaginary power? And yet we will find that this is a very simple problem, and we will be able to generate the answer in our last video coming up.